Now let's start with the um, subject proper for economic operations, as we're done with the overview of the Philippine power system. Now always remember that the power system is a quadratic problem. Generator cost functions are actually quadratic functions when you look at it, and if you read a lot of references, they're all represent the cost of per megawatt output of a generator is actually represented as a quadratic equation. Losses also are quadratic. Remember that the formula for megawatt losses is actually I squared R, so that in itself is already quadratic. Power flow equations, particularly in our AC power system, they are not linear. So technically, optimal power flow and economic dispatch is a math problem that is of a quadratic representation. Let's move on to discussing what is really economic operation of power systems. One of the objectives of power system planners and operators is to minimize the cost of operating a power system. Obviously, we always want to have the cheapest cost available to us, and that includes planners, scheduling, and operating the power system at the least cost manner. Remember that a power system is composed of the following components. You have generators, customer feeders or loads, transmission lines, transformers, shunt capacitors, shunt reactors, breakers, and synchronous condensers. And there's a lot more in the power system. Now, of all those components, generating units have the major contribution in operating costs, particularly because it needs fuel for it to run. Fuel can be coal, natural gas, diesel or oil, and because fuel prices are volatile and dictated by market forces, it's one of the major factors where we have to consider what generation we are operating, because we have to also know what prices we are actually um, are we getting. Although hydro plants are cheaper because technically doesn't use fuel but just depends on water, but its availability is inferior, particularly in dry season, other than those plants that utilizes conventional fuel. So those conventional plants, as mentioned, like coal and natural gas, are more dependable because you have stocks of fuel that can last you for a period of time. Now, what's the main objective of economically operating a power system? You have to optimize controllable power system variables to achieve a desired objective. Most optimization objectives involve you have to decide, do you want to minimize generator operating costs? Do you want to minimize copper loss? Or are you optimizing transmission or distribution configuration? So normally have to have an objective or a goal whenever you're trying to operate a power system, economically again, operate a power system. Now, what are the variables that you can control so that you ensure that you can economically operate a power system? Generators' active power output, which are their megawatts. You can also control a generator's reactive power output, or their MVAR, so that you obviously can improve power flow. Power system configuration through breaker configuration, but this is a more difficult optimization scheme because you can't do it dynamically every so often, where you have the status of power system components to be on or off. Now, what is optimization? Optimization, as defined, is the action of making the best or most effective use of a situation or resource. In mathematical equations, this means solving power systems in which one seeks to minimize or maximize a real function by systematically choosing the values of real or integer variables within an allowed set. Now, sometimes people use brute force to find the optimal solution to a problem. However, it's not appropriate for large-scale and realistic problem because when you're using brute force, essentially you're doing some kind of manual process which may take you some time and some more iterations to achieve your final goal, and it may not be that process may not be very efficient long term for a large scale system. Now, during the course of this course, we will be discussing different optimization techniques. We have the conventional methods as listed here, but primarily we'll be using only unconstrained optimization, which is actually the basic type of optimization where you're trying to optimize a certain problem with only the objective in place, but technically you're not considering any limitations or constraints. This is a great start uh, for analysis so that you understand better um, what would have been the result or this should there be no constraint. So this provides a great baseline for all optimization problems. The most used type of optimization method is in the power system right now is linear programming because you're trying to solve a lot of problems using line equations only. We also have quadratic programming, generalized reduced gradient method, the Newton method, and the mixed integer programming method. Now, all those highlighted in red, we will be covering during the course of this term. There are other intelligent methods. Personally, I've only handled artificial neural network and evolutionary programming, but there's also particle swarm optimization. Artificial neural network tries to mimic the actions of the brain, where you have obviously our brain is trying to in the aspect of gaining a lot of information through experiences and knowledge, and to eventually decide on a better outcome based on certain experiences. So it uses that kind of in that analogy, it uses that kind of approach to eventually determine the probable output for a certain condition. Evolutionary programming makes use of um, let me make this analogy of trying to get your data, trying to manage your data by establishing relationships, and which relationships have the strongest um which of those relationships are forming the strongest link will be used further in determining future outcomes. So it's like the use of that term survival of the fittest. We have also probabilistic optimization such as probabilistic optimization using fuzzy set and analytic hierarchical process. As was mentioned, the unconstrained optimization serves as basis for constrained optimization formulation. There's no constraints because you're not assuming any transmission limits or generator limits. So we will actually use this later on when we try to solve economic operation problems in power systems. Approaches used are gradient method, line search, and the Lagrange multiplier method. Now, for linear program is mostly used by a lot of industries or jurisdiction around the world because it's always simpler to solve linear equations. Now, what it does is the power system problem, which is again quadratic, is being linearized. So it linearizes nonlinear equations to eventually form a set of equations that has, again, you has two major components. You have to have the objective, and you have to have the constraint. Now, linear programming obviously has reliable convergence, and it's very easy to formulate and very fast once linearization is performed. But throughout a lot of studies, this linearization creates some approximation inaccuracies, particularly in the area of line losses, because you're trying to again linearize a function that is again quadratic. So some steps to eventually mitigate this issue is what we call incorporating piecewise linear equations, where you're trying to set up a lot of line equations to represent a certain quadratic function. So it's always, again, the notion there is it's always easy to solve linear equations. Nevertheless, its precision is generally acceptable for most application. Technically, the WESM, or the wholesale electricity spot market here in the Philippines, uses linear programming solution to optimize schedules and derive processes for um, the results of the market. Nonlinear programming handles obviously nonlinear equations in the problem solution. It requires a good approximation of a starting point to start. So you have to have a good starting point. It's more accurate actually because you're already incorporating your quadratic equation. So it's more accurate than linear programming, since you're not linearizing or approximating anything, but it's generally slower than LP. But as of recently, there are a lot of technologies now that aims to speed up these quadratic or nonlinear programming functions. And the only difficult part there is actually harder to formulate.